So what we are trying to do today is working on the notion of compositional rule of inference, and this is a component where we are going to integrate most of the knowledge we have seen so far in the course, and we are going to make use of it for defining the decision-making process using fuzzy logic systems. So during this presentation and during this work that we are doing here, we are going to utilize all the knowledge that we have captured so far in terms of definition of a fuzzy set, in terms of the definition of relation, in terms of operations, in terms of extension principle, and we are going to capture most of these type of definitions that we have seen and the type of theoretical representation of these type of operators on fuzzy logic systems to define the next components of this course, which is going to be related to compositional rule of inference. So what we are going to do in this part of the course, we are going to see how we are going to create what is known as the knowledge base. So when we speak of the knowledge base, we speak of the engine that is going to operate the system that we are going to define. So let me describe for you a system here, okay? So let's suppose that we have our particular process here. So this is process P. This process P is generating certain type of outputs, and this output should be a controlled type of output. And then this controlled output is going to go to an engine. This engine is defined by a knowledge base given by K, and the K is going to utilize and it's going to ingest the information that came to it from the output of the process and then return it back in a feedback loop to the process of the system. If the system, if the process is not generating the adequate type of output, then this K, this knowledge base system, which is the fuzzy logic controller, if we would like to call it, is going to take that particular output of the process, which become the input to K, and it's going to provide certain type of signal to make sure that the process generates the adequate type of output. So that knowledge base is going to be known as K. And this K is composed of an integrated set of relation. Each one of them is composed by an if-then rule type of representation. So you have here R1, and then you have Rn. So these type of relations, the compounded relations are going to represent what is known as the knowledge base K. So each rule is a fuzzy relation employing the if-then fuzzy implication, which we have seen few slides ago. So we are going to see what is the impact of this particular type of knowledge base, or what we call the fuzzy logic engine, on the overall system that is provided to us. Within the provided to us. So I don't know what's happening here. Provided to us to make sure that we are in full control of the process. When all individual rules relations are aggregated, executed, they result in one fuzzy relation represented by a fuzzy set, say K, and multivariable membership functions. So this particular engine K, when we are executing it, basically all the rules are going to be executed at the same time. But there is an overall type of relation that is going to be a compounded one, an aggregate type of relation that is going to be representative of this particular type of knowledge engine. A fuzzy inference. In a fuzzy decision-making process, the rule base K is first collectively matched with the available data. So what we have here, we have an engine K, okay? And this engine K is going to have, as its input, some context or the data context. So this is basically the data context that is going to be the input of this knowledge engine, because a knowledge engine without an input is not going to do anything. So if you don't put oil in your engine, the system is not going to work. So data is going to be the oil of the engine, and the engine itself is all the structure, is all the mechanics that is happening within the systems, where you have interconnected components within the engine that are going to generate ultimately at the outset a certain set of an output behavior for this particular system. And this type of process is known as the compositional rule of inference. So here we have the context, the D, here we have the engine, and when they are compounded with each other, they are going to generate what is known as an output of the system, and this is based on what is known as the compositional rule of inference. So this is the title of this particular component of the course, which is very, very important, and on which we are going to build later on the next part of the course when we are going to look at fuzzy inferencing mechanism. So let's look at this particular system in a mathematical type of framework. Suppose that the available data, which we call it also context, this is the actual data that the system is receiving as an input to the model. So let's suppose that that particular system is receiving a certain set of input. So let's suppose that this particular engine here, so we have the engine in this particular setting, so the engine, so the engine here, engine K. So this engine K is going to receive the context. So it's going to be subject to the context, and the context is going to generate the compositional rule of inference part, which is given by I. So I is known as the inference components of the system. So suppose that the available data is denoted by a fuzzy set or a relation, which is given by D. So this is the context, okay? And this is the engine. In order for us to obtain this particular inference, I mean the compound inference components, which is known as inference I, which is known as the inference I, we are going to subject the data to the engine. So basically the engine is going to receive the input, and the outcome is going to be the composition of these data with the engine itself. And we are going to see certain type of operations here to do the computation. And without going into the mathematical details of this particular representation, we are going to define at least 2 or 3 operations that are providing us with this particular type of inferencing mechanism. So this is the first part, which is going to provide us the decision-making process for that particular system. In this compositional rule of inference, we can define it in the form of a membership function as what is known supremum or max. So we can utilize in certain book, I mean the max over all the y's. Y is going to be the component that is going to be the component that is common between the D and the K. So this is going to be the interface in this particular region. And we are going to see an example in the next few slides. So this is the maximum of min of mu D and mu K. Remember, mu K now is a set of the relation, which is the engine itself, which is the engine that is produced by all these type of if-then rules. And the mu D is no other than the context or the input of the data. And we are going to see an example in a few moments. So inference I, which is denoted by I, is the output of the knowledge-based decision system. Remember that this particular output of the engine is going to be itself the input of the process. So the inference is going now to go to the process and is going to subject it to certain type of change. And the process is going to give us, an output, and that output is going to go in feedback loop again to the engine. So this is done in a feedback loop, similar to what we have seen in the area of control when we are having the plant. Remember, in a control system, we have the plant or the process, we have the output, we have, for a regulation type of control system, we have a regulating type of signal here. Okay, and here we have a feedback loop, and in the feedback loop, we have what is known as transfer function of the system, the feedback transfer function of the system. So this is transfer function. and then this transfer function is going to be the one of the inputs of this comparator. So this is basically the system is receiving some feedback and it's receiving some part from the standard type of signals so that it creates an error. That error is going to go on actuator, which is going to activate the plant. So this is in the area of control system. This is exactly the same process here. So we have the inference here, the decision of the knowledge engine, and then it's going to go to the plant to provide to the plant, the output of the plant is going to be the input of the inference engine. So this is what is known as the soup mean, or what we call also max mean composition. So when I speak of max mean composition, it means this particular compounded type of relationship that we are doing between the data and the knowledge engine. So this is known as the soup mean or max mean composition. Another method to compute the inference I is through the soup product. Remember that the mean here the mean is the T, the default of the T norm operator for a particular system. So the mean could also be the product in the representation in the form of the T norm. So product, the mean are all of them T norm operators, as we have seen in previous slides. So these are T norm. So whether we represent mean or product or T norm, so it's, all of them depend on what you are utilizing and what you are told to do in this particular type of implementation. If you are not told what type of composition rule of inference to utilize, then immediately utilize the max mean composition rule of inference. So this is what is known as the soup product, and this is what is known as the max mean type of composition rule of inference. Okay, so let me give you an example here. So let's suppose that we are having a system and this particular process, is generating certain value for the C. So this is A here, okay. Okay, so fuzzy set A represents the outputs. So this is, the engine K here. So let me talk. So this is here. The process P, as we discussed, and the process P has an output as A and an input as the value of C. So C is the output of K and A is the input of the knowledge engine. However, C is also the input to the process and is A is the output of the process itself. So let's suppose that we have fuzzy set A of universe Y representing the output of a process P, similar to this representation. The fuzzy set C of universe Z represents the control input to the process. So let's see the relationship that is, driving this particular type of process. So we have the output of the system as A and the input is C, but A is also the input and the C is the output. So for K, we are going to utilize A implies C. So this is for the engine K, okay? So for this particular type of engine, in order for us to create this relationship, as we have seen, the minimum operation that we are utilizing when we are dealing with the implication type of operators, or the relation between A and C, where A is the antecedent and C is the consequent. So what we do, we create this particular matrix where the Yi, which is representative of A, and the Zj here, so this could be Zj here, is the representation of the, so this is the A here, and this is the C. Okay, and we would like to see all the type of relations that are in between the input or the antecedent A and the output of the engine K. So this is for this particular engine K. So what we do, we take the minimum of each one of these particular components. So Y1 and Z1. So we take the minimum, and the minimum operation is going to provide us with the value of 0 here. And then we take the minimum for the last elements for Z equal to 4 and Y equal to 5. So we look at it here and we take the minimum between both of them here, and this gives us this particular element. and we do it for all the element of matrix, as you can see here. So it's 5 by 4 type of matrix for this particular type of representation. So I would like you to understand this particular fact, I mean, because it is going to be an important component for the definition of these type of relationships. So that's how we construct a relationship that is between an input and an output. So this is what it is known as a relation. And as you can see here, we have, I mean, an if-then rule. So if A, then C. So we are utilizing here only one single rule, okay? In the general case, we are going to utilize several type of rules, and I'm going to show you later on in the next part of our course how to utilize this K when we are dealing with several type of relation. But for now, I would like you to stick with this type of representation. So this is the engine K. We have defined now the engine K as this particular type of matrix. So now let's do something. So now remember, now this is the K, we have defined it. So now, given a certain type of context, A0, we would like now to utilize, I mean, what is the value of, given A0, which is going to, the context, okay? So this is the context, the new context. So the new context or the data, we would like to find what is the value of what is known as C prime, which is going to be the output of the system. So this is like we are defining a temperature here, a warm temperature, okay, warm temperature, and this is an air conditioner type of output for this particular system. So this is the relation that we have defined between the warmth and the air conditioner, and now we would like to see for a particular temperature of the warm temperature or components of the warm, what is the compound value for the air conditioner, and that we are going to utilize it using the composition rule of inference. So this is the fuzzy sets, which is going to be the context. This is the data that we define as, for instance, a part of a warm. So this is a component of the warm temperature, part of the realization of the warm temperature at a certain amount of time. So warm is general, but we could take, I mean, components of the warm. So if you have warm type of representation like this in the continuous case, then at a particular time, we have value here located at this particular level of the warmth type of membership function. So this is the continuous and this is the discrete representation. As you can see here, we are defining the warmth as the 0.8 value at the support of Y4. Remember that this particular membership function in the discrete case, and we have for Y1, so we have for Y2 here, we have for Y3 here, Y4 and Y5. So all of the values for the support of the warm temperature are equal to 0. The only one is going to be 0.8. Okay, so given this particular context, what is the value of the C prime? And we utilize exactly the notion of what we have defined earlier. This is the equivalent of what we have seen earlier in the form of D compounded with K. Okay, because the relation here R is the equivalent of the K. And this is defined as C prime. So let's look now at the compositional rule of inference, utilizing the sup min representation, how to compute this particular value. So sup min, so this is the maximum of the min. So this is how we compute it when we are dealing with this particular representation. First of all, you transfer the data context, the context of the input of the system into this vectorial type of representation. Remember, this is A0, okay? This is the A0, this is the context, and this is the relation R. Okay, so how we do it, the sup min, here we have all the y's, I mean on, so this is the maximum over all the rows. So this is the yi here, okay? So we are going to take all the elements. So first of all, we are going to do the minimum. So the minimum of all the columns. So we have column 1 and column of R. So here, the minimum of this column and this column. And then the minimum here and the minimum with the second column here. Okay. Once we do that, then we are going to take the maximum over the rows, which are of course, over all y's. So this is how we do the representation. So first of all, column A0 and this column. So we check the minimum values between this one and this one. So here 0 and 0, 0 and 0, 1, so it gives us 0 here. 0 and 0, 1, it gives us 0. Here 0, 8 and 0, 1, it gives us 0.1. And 0 and 0, 1, it gives us the minimum of 0. So this particular matrix that we have compounded here by finding the minimum between A0 and this first column is what we have here. Okay, and then we do the same thing. So we compare A0 with the second column. We obtain this particular column here. And then we compare it with the third column and we obtain this one here. And then we obtain it with the fourth column and we obtain this particular column here. So the minimum of all the columns is this particular matrix here. Okay, and now what we are going to do, we are going to do the maximum over the rows. So what we are going to do, we are going to take the maximum. So we go from one row to the next, to the next, to the next, and we take the maximum. So if we go to the maximum of all these rows for the first elements, so we obtain 0.1, because the maximum of all these elements 0.1. The same thing, the maximum of all these elements is 0.7. The maximum of all these elements is 0.8, and the maximum for all these elements is going to be 0.4. And this gives us the outcome of that particular data context as applied to the engine. So the engine now, I mean, receiving A0 as an input is going to generate C prime as an output. And this C prime is going immediately to the process, and it's going to excite this process so that we develop, I mean, this particular element here. So this particular element could be a measurement of a sensor. If the temperature is as we expected, then the K is not doing any type of operation. If the temperature is different than what we are expecting, then we are going to have K is going to do certain type of operation, generating another C prime, and then it's going to affect the process. So the process is like a room. This room has a controller. It has a sensory component. So the sensory components and the output of the system. So the sensory is going to measure the output, what the system has output at that particular instant of time. And that sensory type of measurement is going to excite the controller, which is the value of K, which is the engine K. So here we have a process and we have a decision maker, which is in the form of K. The decision maker, K, is going to take the input and generate an output that is going to excite the process and so on and so forth until the system is completely regulated in terms of temperature or in terms of humidity or in terms of pressure. So this is an example for the utilization of the max main composition rule of inference. Let's look at the max product of the composition rule of inference. So for the max product, we have to change the representation of this particular element into this particular format. So first of all, the vector now is in the row format and the matrix is in the row and the column format. Why? Because if we are going to keep this as a vector, so let's say it is 5 by 1, and then we multiply this vector here, or this matrix, a vector is a matrix, times 5 by 4, this is not feasible, this is not compatible, so we cannot do this, okay? So this cannot be done. So we have to represent this vector in the form of 1 times 5, so it's a row vector times 5 times 4. And the outcome is going to be 1 by 4, okay? So the same thing what we mentioned earlier, so the y is going to be the common element is going to be the y. So you can see the y is the common element, and that's why we take, I mean, the maximum or the supremum over all these particular elements of the rows. So the rows are no other than the y components. So the y is no other than the common type of variable in between the two vectors, between the vector of the input and the matrix itself. So that's why we are computing. And of course here, I mean, vector times, I mean, the column. So we end up with 0.08 here. This is due to this product of 0.01 times 0.8. So it gives us 0.08. And this element here, 0.56 is 0.8 times 0 is this particular element. The same thing for 0.64. It's due to this product of 0.8 times 0.8. And finally 0.32, this times 0.8. So this is how we are composing the system. And now we are going to take the maximum of this particular row. Of course, we have one single row, so that is going to be the results of the system, and it's going to be represented in the form of C prime. So these are the two types of operation which help us during this particular type of process for generating the compositional rule of inference. So this is the inferencing mechanism. This is the decision-making process that is provided to us by the engine K to provide us what the system has to generate for the process so that the process is going to be activated and it keeps operational under certain type of framework that is defined by this particular knowledge engine. So we are going to see more complex type of representation of this system for continuous representation of membership functions and other type of representation. Let me go here for other type of representation for this type of compositional rule of inference. So the supremum of the minimum or supremum of the product could be generalized to more type of representation. So it could become supremum of T norm. So in general, any sup T operator can be used to perform the compositional rule of inference where T is a T norm. So it could be the Zada T norm operator, it could be the Mamdani T norm operator, it could be any type of T norm operator. If you are not told what type of operator you are utilizing, because each one of these sup T operator is related to a particular type of problem. So if your designer tells you that I would like to utilize any type of generic type of composition rule of inference, then immediately use the max mean. Okay, so in an example, in an exam or in a quiz or whatever, I mean, or in the assignment, so the max mean is the default type of representation for the composition. Of course, max is exactly the same as the supremum in the context of this course. Although mathematically speaking, they are not exactly the same, but in the context of fuzzy logic system and the context of this course, max or sup are exactly the same. So sup min and sup product are a representation of the sup T, because the product is a T norm, the minimum is a T norm, and they are special cases of the supreme T norm. So now let's go beyond this and let's talk about what is known as sup T and inf S compositions in general cases when we are dealing with two type of fuzzy set that are represented by two membership functions type of relations. First of all, when we are doing compositional of rule of inference, usually we have to have at least one of the element has to be common. Otherwise, we are not able to do this type of composition. Okay, so this has to be commonality between two elements. And the commonality, it means that this is the consequent for this particular relation, and this is the antecedent. So when you are fusing two type of relations, the consequent of the first relation has to have the same dimension and it has the same variable as the antecedent of the second relation. That's one of the major type of requirements that you need to do for doing these type of compositions. So we talk about a number of representation here. So there is what is known as the sup T composition. So this is the general case. So look at this is the common representation. So this is the supremum Z belong to Z. In the previous case, it was the Y. So here we are generalizing. So it's X, Z, and Y. So here the supremum of the minimum or the T operation. So first of all, you have to create the T norm between these two type of operations, two type of relations, and then take the supremum over all the common values for the Z belonging to the universe of discourse Z. We also define another type of composition which is not very much used, which is the dual representation of the soup T composition, and it is known as the nth S. So it's called the nth S. So the nth is the dual of the soup primum, and the S is the dual of the T norm. So this is the T norm, and this is the max or soup. Okay. So as you can see, this is a dual type of operation. So the dual type of operation, as you can see it here, is denoted by this particular type of sign. So the dual operation P nth S composition is given by nth, which is the minimum equivalent. So this is the minimum or the T type of operation here, and mu P X Z, as you can see, the common elements. But here we have the S norm. Okay, so they are connected. So it is min and S. Here it's soup and T. So we have to be very careful when we are dealing with this supremum of T norm and infimum of S norm type of representation. Okay, let's look at some of the connections between these type of relations. So for the commutativity, for the soup T or nth S, so we have the commutativity operation. For the associativity also, both of them have the same type of representation. The associativity type of rules applies to them. Distributivity as well, it applies for both of them. And then we have De Morgan's law. So De Morgan's law, it tells us that P composed with R is no other than complement of P and complement of R, while we have the dual operation. So if this is the soup T, this is the nth T of this De Morgan's law. The same thing we have here, P, I mean nth S is equal to the P bar, the complement of P, composed with R bar, which is composition rule of inference, which is given by the soup T that we have seen earlier. So that's the type of connection that is combining the two type of composition rule of inference. So nth S or soup T are two type of composition rule of inference. They are utilized in various type of application, and you are usually told what type of operation that you are going to utilize for the composition rule of inference. If it is the soup min, then utilize the first one that we have seen. If it's the nth S, then utilize the nth S operation as we have seen it in this particular type of slides. Okay, let's look at this particular case study, and this is an example of what we want to see in this type of relations that we are seeing. So we are putting here a relation that is connecting between two universes of discourse between X and Y, where X has 5 elements of support and Y has 5 elements of support, and the relation, similar to what we defined earlier, came to this particular representation in the format of a table or in the format of a matrix, and it is a fuzzy relation that is connecting between this, the defined in X across Y, which is the Cartesian product, and it is X implies Y. So this is basically an implication operation, and this particular implication operator provided us with this particular relation that is defined in the matrix form. So this particular relation, which is given by Rxy, Xi, Yj, is given by this particular type of relation. So now let's do a certain number of operation on this type of relation, and in order to illustrate several type of the concepts that we have seen in the previous slides. So we are going to define the AXI, which is the projection onto Xi of this particular relation. We are going to define the Byj, which is the projection onto Yj of Rxyj. So if we look here, so the Ax is going to be a vectorial type of representation where we take the maximum over each one of the rows over all the values of Y. So this is a projection onto Y. So first we are going to see the maximum, and this is the maximum for this particular element. This is the maximum for this particular element. The maximum here and the maximum here, it occurs that all the maximum occurs at one particular element, which is at the value of y2 is equal to 2. So this is by coincidence, but that is going to be the case for this particular example. So this is the definition as we are doing it. And then we take the notion of A1xi. So what is A1xi? So it is the value at the first y, at the support of y is equal to 1 for all the values of xi. So we define it in this manner. So what do we mean by that? So we go here, this is the support for y is equal to 1, and we define it for all the values of x. This is basically what is the A1xi. A2xi is no other than the same thing, but now we go to the support number 2 for the value. So this is the support number 2, and all these particular values represent the set. So this is A1, and this is set A2. Okay, A2. This is the set A2. Okay. So let's now have these type of definitions, and let's do some of the type of operations that we have seen in the course earlier. So we would like to have AXG, we would like to have the A1XI, so which we have just defined, B2, BYJ. What is the notion of A1, which we have defined here, union A2, A1 intersected A2. What is the alpha cat for A1? What is for the value of alpha is equal to 0.2, 0.42, and 0.5. So what is the alpha cat of A1? What is the alpha cat of a discrete set in this particular type of representation? What does that mean, the alpha cat of a discrete set? What is the membership function of this particular type of alpha cat? So we are going to define all this type of representation. And then we would like to define the notion of implication, the notion of Cartesian product between A and B, and then the cylindrical extension for xy, okay, and then the cylindrical extension of B into xy. And then we are going to see the extension principle for this particular type of relation defined by z is equal to x plus y, and we would like to do the sketching of C. So all of this is going to be the subject of the next few slides. So I'm going to go, quite briefly on these ones, and you have enough time to look at them at your comfort there. Okay, so let's look at the AXI. So as I mentioned to you, the AXI is the projection onto xi for all the values of Rxi, yj. So this is the supremum over all the value of yj for mu Rxi, yj, which is the table that we have seen earlier, and that gives us rise to this particular type of relation. Remember, this is the projection onto x, as I mentioned to you, by taking the maximum over all y's for this particular relation onto x. So this is onto x. So again, we go and we take find the maximum here, 0.7, 0.8, 1, 0.9, 0.5. And as we have seen in previous lecture, when we have a relation that is in the 2D or 3D type of 2D type of format, when we are doing the projection, we are going to end up with the 1D type of format. So from 3D representation to 2D representation of a membership function, as we are going to see it. So a representation in 3D, it means that you have x, y, and then you have the surface. And then we are going to utilize the projection of that particular surface to give us a membership function into the 2D, as we are going to see it now. So this is the projection of all that table or that matrix. So this is what we are obtaining, and these are the representation of a discrete representation of a fuzzy set. So the projection of a relation is a fuzzy set. That's what we have seen, and this fuzzy set is given by a membership function given by this particular type of representation. Okay, so the membership function here for A1, so we go to the value of where the y is given by the value of 1, and we end up to find this particular type of representation, and these are the discrete representation. So usually we showcase, the fuzzy sets, in discrete format like these. So these type connected between all these type of spikes, but usually, regularly, we do, these are the spikes representing the membership function, okay? So we connect them to give us the curve, but usually this is how it is obtained. And these are the representation of a discrete fuzzy set, as we have seen it in the course. The same thing for A2. So this is the location where y is equal to 2 for all the values of xi. Okay, so this is vertical type of representation for the system in the xi dimension. Okay, so let's look at the by yj. So we are projecting here onto y for all the values of x. So let me go back now to our matrix here, or our table, and as we did for the x's, so now we are going to do it for the y's. So what we are going to do, we are going to take the maximum over all the x's here. So all the x's, and we are projecting them onto y. So the maximum here over all the x's for this particular system is going to be 0.6. The maximum here is going to be 0.7. The maximum here is going to be 1. Maximum here is going to be 0.7. Maximum here is going to be 0.4. So this is projecting onto y, and this gives us the value of b for that particular representation. Okay, so the byj is given by this, fuzzy sets. Again, it's represented by these spikes here. Okay, which represent the membership function as given here. Okay, so we are able here to extract from the relation that is, x and y, Cartesian product, this particular type of representation, and this is an example on how to obtain the projection onto a system that is in the discrete form. A1 and AU2, so now we have two sets, and we have seen the definition of the union of two sets. So basically we take the maximum out of the two membership function. We have seen that before. So the union, if I don't tell you what type of operator you are going to use, then immediately use the default operation. So in a quiz, if I give you a quiz and I don't tell you what is the S-norm operation that we are using for a particular system, then immediately use the default operator, which is the maximum. So here, the system provides us with this particular representation again. So these are spikes, okay? And this is the type of representation for this system. The same thing for A intersects A2. This is the default T-norm. And as we did it, so we compute the smallest among the A1 and A2, and it gives us these particular type of values. Okay, so 0.4, 0.5, 5, 0.7, 0.4, 0.1. Okay, the membership function now. So this is first what we are going to define. So this is a little bit tricky in the form of the alpha cat. So there is the alpha cat itself. Remember, the alpha cat of a membership function is the interval over the universe of discourse, which is higher than a particular value known as alpha. So if this is the alpha cat, so then we take all values, the interval for all values that are greater than alpha. So this is the interval, and it is discrete representation. So in this particular case, the alpha cat is this interval, but the alpha cat also, so this is the alpha cat of this particular, representation. So this is the alpha cat, okay? So the alpha cat is a crisp set. Now, if we would like to have the membership of the alpha cat itself, so the membership function is going to be a discrete function in this particular case. So the membership function, because it is a crisp set, is going to be the interval with its maximum value at 1. So this is the interval here, and this is the mu of the alpha cat. Okay, so the alpha cat is a crisp set of the fuzzy function. The mu alpha cat also is a membership function, but it takes values that are maximum within the interval and 0, so it goes discretely here to the value of 0. The same thing occurs when we are dealing with a system that is, so let me go back here and do. Okay, so let me do this. Okay. So the same thing, if we have, elements here, of alpha cat. Okay. And if we define the alpha cat of a particular system, which is located here, so we take all the values where they are higher in this particular representation, and we have it in this interval. Okay, once we have the interval, then we can take the equivalent of the interval. Now it becomes this particular, so here. So this is the alpha cat here for this discrete representation, and this is the mu of the alpha cat for this particular example, and that mu is going to give us the value of 1. Okay, so this is the alpha cat of a discrete set. Okay, so because alpha cat is a discrete set. So this is what we have here. The exact same thing here, we are doing it. So here we are trying to find the alpha cat of a system membership function for the alpha cat, which is equal to 1 for mu f greater or equal than alpha, and equal to 0 for mu f less or equal than alpha. So let's look at the alpha cat for the system when we have alpha is equal to 0.2. So let's look at A1. So what is the value of A1? So let's go back to A1 and see the representation of A1. Look at A1, okay? And look at the 0.2 here, okay? So 0.2 occurs around this particular area, 0.2. Okay, so we go and we check which membership function are higher than these values. So we have this value here, we have this value here, we have this value here. So this is basically the interval for the alpha cat, for the value alpha 0.2. Okay, so that's the alpha cat. Now, if we would like to take the membership function of it, then the membership function is going to be this particular representation, which we found it, more cleanly in this particular representation here, as you can see. So for all these elements, they have values that are greater than 0.2, 1, 1, 1, 1. That is because each one of them is higher than 0.2. And then we have 0 because only the last element here has a value of 0.1, remember? So because it is less than the alpha cat, then we have this membership function. So there are two things that I would like you to remember. The alpha cat is different than the membership function of the alpha cat. So the alpha cat provides you with the interval where it is located. So that's an interval type of values between 0 and 3. So that's basically the alpha cat. Now, the membership function of the alpha cat is a membership function in the usual sense. So it has basically values that are higher than 1. So usually here, because this is, a discrete representation, so we can also represent it in this particular type of format for this particular system. But this is, the interval for all of them. And in order to compound all of these particular values, the representation of the alpha cat is going to be this continuous representation. So it's going to be this representation. Okay. So that's what it is for the membership for the alpha cat. So the same thing for alpha is equal to 0.42. We know that only the two values that have alpha that are higher than 0.42. So we have only this particular interval, which satisfies value that are higher than 0.42. So we create for it its membership function. So this is the membership function, as you can see here, the membership function of this particular interval. So the membership function of an alpha cat is a membership function that has maximum value of 1 and minimum value of 0. So discrete type of values. Let's continue. So this is for 0.5, the same thing as the earlier one. Okay. So now let's look at the membership function for all the values that are minimum mu axi and mu byj. So remember that we have created out of the original table membership function of the fuzzy sets mu ab, mu a, and mu b. So now what we do, we go to A and B, and then simply we take the minimum of each one. So this is x1 and y1. x1 and y1, the minimum is going to be here. Okay, for x2 and y1, x2, and so this is y0 actually. So let's start with y0, and this is x0. So x1 and y1 minimum is equal to 0.6. So this is the minimum for both. And then we continue for x4, okay, so which is going to be located here, and y1, so we obtain the value that is going to be given. So this is here, and this one contribute to this particular, no, actually, sorry for that. I did not mean that. That particular element has to be minimum between the x and y0. Okay, so this particular element that I just mentioned here should be located here. So the minimum of x4 and y4 is going to be equal to 0.4. So this is how we construct the A implies B, which is the relation of A implies B. If A, then B. This is the type of relation similar to the earlier part that we have seen during today's lecture. So similar to the representation of the K when we have taken the A and the C and we constructed our relation between the two of them. The same thing, so this is the graphical representation for it, okay? We do the same thing for the Cartesian product, which has exactly also the same thing. So we obtain the same relation as, because we know that the Cartesian product is no other, I mean, an operation which is equivalent to an implication. Remember, the implication occurs within a Cartesian product of A cross B. So they are the same, exact same type of operations. So this is the exact same matrix that we have computed a few seconds ago. Okay, so this is the representation, and the representation in the particular form is exactly the same as the earlier relation. Now let's look at the notion of cylindrical extension of A. So cylindrical extension of A, so we have the A, which is here, and we would like to extend it into a cylindrical type of representation. Okay, so it gives us this particular representation. So we are extending the xi over all the yj's. So this is cylindrical extension of x to y, x to y. Okay, so that's basically what we have in this representation, and we do the same thing. So this is cylindrical extension of x, so you can see this has been extended all over the y. So that's a cylindrical extension over y. We do the same thing for cylindrical extension of y to x. So we take this row, which is the y representation, and we expand it on x's. This is a cylindrical extension, as we have seen the definition in the earlier type of lecture. Okay, and this is the representation of it. So this is, we are extending this onto, the direction of x. Okay, let's look now at the last example for this set of problems that I wanted to showcase you the various type of operation. So now we would like to utilize the extension principle for the crisp relation of z is equal to x plus y. So we have, remember, we have the x and we have the y, okay? So they are representative of two universes of discourse. And now we would like to have all elements that are subjected to the z of x and y. So basically it's another axis that we are going to define as a cylindrical extension for all the elements of x and y. So let's look how we are going to create this particular representation. So the extension principle here for this particular system, we are going to look at all the relation between the elements of x, I, and yj, and we are going to look at the supremum of this particular relation for the elements over z equal to x plus y, for all the elements that are, perpendicular to each other, x and y. So this, we would like to have it in the form of CZK. So CZK is no other than the mapping that we are doing it for a relation, which is given by x plus y. Okay, so I'm going to show it to you how to obtain it in this particular representation. So note that the diagonal broken lines are the x plus y is equal to z. So let's do and look at the graphical representation here. Remember, this is the representation of y, and this is the representation of x. Okay, so when we are going to speak about all the x's and y, so x and y, of course, so we are not going to do the summation of x and y. So this is basically, it's like the maximum values over x and y. And x and y is no other than the diagonal, because here when we take it, I mean, this particular way for y equal to 3 and for x3, so we go for all the region of y's and the x's. So y and the x's, the y and the x's. So that's the best way for representing the x and y. Again, when we go through this particular representation, this is going to showcase us that we are going through the x's and y. As you can see here, we go for this one, we go for this one. In order to showcase that we are going over x and y, so we do it over the diagonal, because the diagonal not only, I mean, it showcases it's for y and for x, for y and for x, for each one of the column, for y and for x. The same thing for this particular value here. So we are computing all the values for this particular system here, y and x. Okay, so for this particular diagonal, so we do it in this particular way. The same thing we do it for this particular representation for y0 and the x3. So we start from y0, so this is y0 and x3, y1 and x2, y2 and x1, y3 and x0. So all of this provide us with the means for creating the compositional rule, not the composition, but this extension principle of this particular type of mapping. Once we have achieved this particular type of dotted line, then we are going to take the maximum. The maximum is going to be representative of this particular type of y. So the maximum between x and y. So let's look at the maximum here. Maximum here is equal to 0.4. Maximum here is equal to 0.7. Maximum here is equal to 0.9. Maximum here is equal to 1. Maximum here is 0.8. Maximum here is 0.7. Maximum here is 0.4. And maximum here is given by the value of 0. So all of these particular values, we are going to, map them into this particular mapping, as we have seen when we have talked about the extension principle. Okay, so the extension principle provides us with this particular operation that we are doing between x and y. We have seen earlier that we do an extension principle over one particular fuzzy set. So here we are doing it over a relation between x and y. And this is what we are obtaining in this particular representation. So this is CZK, and it gives us all these particular values that are for all the system that are provided for these particular type of values for the model. And as you can see, the dimension is higher than the dimension of x and higher than the dimension of y. Basically, they are the summation of y, x, and y, as you recall. So these are all the particular values that we are doing for all these particular representation for our system. Okay, so that's what I wanted to share with you here in this particular example. So in the next lecture, we are going to go into more details on a compositional rule of inference and definitions when we are dealing with a system where we are dealing with a continuous representation of a membership function, where we are going to see how to tackle several types of rules that are going to represent this knowledge base given by K. So we are going to talk about all of that in mathematical framework, where we are going to use the notion of projection, where we are going to use also the notion of cylindrical extension, as we are going to see it, to give us the final framework for doing what is known as rule of inference mechanism, and for generic type of representation for a system where the model is provided to us through several type of rules, if then rule type of system. So that's what I wanted to share with you. I mean, in this particular presentation, and I would like to. I will see you on Monday to start on the next slide, which is fuzzy inferencing system, which is the next set of slides that I have posted to you in on the website of our system. So you will find the recording of this lecture on the website of our system. I am ending the lecture here because basically this is another recording of the lecture that I made on Friday, and because of some glitch, I mean, with the team system, the lecture was not recorded, so I have to re-record it. So that's why I haven't had, I mean, I'm not taking questions. I simply did the recording of the lecture of Friday for, I mean, to make it easier for you. I did not want to share with you the slides in this, in the particular formats and with a certain type of marking. So I took the time to explain to you all the elements that I have explained to the students that have attended the Friday lecture. Thank you again, and I'll see you on Monday. Bye.